We are from Roy's Academy faculty team, and today we'll learn Course CBSE Class 10, Subject Mathematics, Chapter 3, Pair of Linear Equations in Two Variables, Topic, Graphical Solutions and Consistency of Linear Pairs. For obtaining similar video explainers, please connect Roy's Academy at 8910890311, repeating the number again, 8910890311. Our another number, 8910600503, repeating the number again, 8910600503. Hey everyone, have you ever wondered how simple, straight lines can actually solve real-world puzzles? Well, that's exactly what we're going to dive into today. We're talking about pairs of linear equations. Now, I know that might sound a little complicated, but trust me, it's really all about telling stories with lines, and we're going to make it super clear.
All right, to really get a handle on this, let's ditch the dry formulas for a minute and take a little trip to a bustling country fair. You're about to see how this kind of math just pops up in everyday life when you least expect it.
Okay, so meet Akila. She's just trying to have a fun day at the fair, but she's accidentally created a pretty interesting puzzle for us. See, she's got two conditions going on. One that connects the number of games she played to the number of rides she took, and another one about the total money she spent. Our job? To figure out the exact number of rides and games she enjoyed.
So how in the world do we solve this? Well, it all starts by translating her fun day at the fair into the language of math. Let's see how her story gets transformed into a couple of equations that we can actually work with.
It's actually a pretty straightforward three-step process. First up, we need some placeholders, right? So let's just call the number of rides X and the number of games Y. Then we take her two conditions and turn them into math. The number of games is half the rides. Boom! That becomes our first equation, y equals 1/2 x. And the total cost being 20 rupees, that gives us our second one. And just like that, we've turned a story into a solvable problem. Now, here is the absolute key, the big idea for today. Every single linear equation, like the two we just made, can be drawn as a perfectly straight line on a graph. So, think of each line as holding all the possible answers for one of the conditions. So, to find the one single answer that makes both conditions true, we just need to find the one spot where those two lines cross paths. This brings up a really cool question. When you draw any two lines on a graph, what can actually happen? It's not unlimited. Turns out there are only three possibilities. Let's explore each one. Okay, case number one, this is the one you'll see most often. The lines just cross at one single point. That point right there is the sweet spot. It's the one unique solution that works for both equations. For Akila, this would be the single combination of rides and games that fits her story. The second possibility is that the lines are parallel. You can think of them like railroad tracks, you know? They run side by side forever, but they will never, ever cross. If our equations give us parallel lines, it means there is no combination in the universe that could possibly satisfy both conditions. There is simply no solution. In the third case, well, it's a little bit of a mindbender. The two lines are coincident, which is just a fancy way of saying they're the exact same line. One is just sitting right on top of the other one. So what does that mean? It means every single point on that line is a solution to both equations. You don't just have one answer, you have infinitely many. Okay, so now that we know what can happen visually when we draw these lines, let's learn the official lingo that mathematicians use to describe these situations. It really just boils down to one simple question. Is there a solution or not? A system of equations is called consistent if it has a solution. That's it. It doesn't care if there's one unique solution, like our intersecting lines, or an infinite number of them, like with our coincident lines. As long as there's at least one answer on the table, we call it consistent. And on the flip side, if a system has no solution whatsoever, we call it inconsistent. This term applies only to that one case we saw, the parallel lines that never meet. It's inconsistent because the two conditions are basically contradicting each other. They can never be true at the same time. So drawing graphs is cool and all, and it's a great way to visualize the problem. But let's be real. It takes time, you need graph paper, you have to be precise. It can be a hassle. What if I told you there's a faster way, a purely algebraic shortcut to know the outcome? Well, there is. Let's get into it. This is the big question, isn't it? Can we predict whether the lines will intersect, be parallel, or be the exact same line just by looking at the equations themselves?
The answer is a huge yes, and it all comes down to comparing a few simple ratios.
And boom, here it is. This table is your secret weapon. For any pair of equations, as long as they're written in that standard ax plus by plus c equals 0 format, all you have to do is compare the ratios of the coefficients. If the ratio of the a's is different from the ratio of the b's, the lines will cross. Guaranteed. If all three ratios are identical, they're the same line. And if the first two match but the third one doesn't, they're parallel. It's like a crystal ball for algebra, no drawing required. All right, enough talk. Let's put this amazing ratio shortcut to the test with a couple of real examples. You're about to see just how fast and powerful this is. Okay, check out these two equations. That second one, yikes, it's got fractions and everything. Imagine trying to graph that accurately. No thank you. But with our shortcut, this is going to be a piece of cake. So let's do the math. The ratio of the a's, a1 over a2, is 5 over 3. Simple. Now the b's. b1 over b2 is negative 8 divided by negative 24 over 5. You do a little bit of fraction magic, and what do you get? 5 over 3 again. And finally, the c's. c1 over c2 is 1 divided by 3 over 5, which is also 5 over 3. Since all three ratios are exactly the same, we know instantly that these are coincident lines. Infinite solutions, done.
Let's try one more. This time it's a word problem about Champa and her shopping spree. Just like with Aquila, we have two different statements that relate the number of pants and skirts she bought. Let's see what the ratio test reveals this time.
First, we translate Champa's shopping story into two equations. Then we just rearrange them into that standard form that we need for our trick. Now, for the moment of truth, the ratio of the a's is 2 over 4, which simplifies to 1/2. The ratio of the b's is negative 1 over negative 1, which is just 1. And wait a second, 1/2 is not equal to 1. We can stop right there. We don't even need to check the third ratio. Our rule tells us these lines intersect, which means there is one unique solution for Champa's puzzle.
So we've seen just how awesome this algebraic shortcut is. But it only tells you if a solution exists and how many there are. It doesn't tell you what the solution actually is. So I'll leave you with a question to think about. When would taking the time to actually draw the graph and find that intersection point be more useful than just using this quick ratio test?
This was an initiative from Roy's Academy faculty team, and today we've learned on course CBSE Class 10, Subject Mathematics, Chapter 3, Pair of Linear Equations in Two Variables, Topic Graphical Solutions and Consistency of Linear Pairs. For obtaining similar video explainers, please connect Roy's Academy at 8910-890311. Repeating the number again, 8910-890311. Or another number, 8910-600-503. Repeating the number again, 8910-600-503.